Math 1332, Chapter 10, Probability and Counting Techniques. Section 4, Tree Diagrams, Tables, and Sample Spaces. Video 2, another example using tree diagrams. A common use for a tree diagram is when you repeat the same experiment over and over and over again, and that experiment is binary, meaning that it can only have one of two outcomes, and those outcomes are equally likely, such as flipping a coin. Suppose you flip a fair coin 4 times in a row, which means there's a 50% chance it comes up heads and a 50% chance it comes up tails, which, by the way, is critical when using a tree diagram to calculate probabilities, because otherwise the final outcomes are not all equally likely. It's possible to do if the outcomes are not equally likely. It's just a little bit beyond what this particular section in this chapter is going to cover. I might do a video at the end to show you how to adjust if the outcomes are not equally likely. But anyway, suppose you flip a fair coin 4 times in a row. Calculate the following probabilities. A, you get all heads or all tails. B, you get the same number of heads as tails. C, you get at least 2 heads. And D, you get at most 1 tail. Well, this experiment consists of 4 quote-unquote decisions to make. What are you going to get on the first coin, the second coin, the third coin, or the fourth coin? And as a consequence, we're going to use a tree diagram. So how do you draw a tree diagram for flipping a coin 4 times in a row? It's actually pretty easy. You start with the with the root on the top, like you do with any tree diagram. And then for the first coin, that's so horrible, I got to write it better. For the first coin, there's only 2 ways it can come up: heads or tails. And then for the second coin, same thing. You branch out from the end of the first coin. Let me make this last branch over here a little bit shorter. I'm kind of anticipating how much room I'm going to need, and the answer is a lot. There we go. Why is my face all the way down there? All right, for the second coin, it can either comes up heads or tails. So from the previous coin's branches, we're going to branch out twice. The second coin can be heads or tails, either over there or over here. And then we do the same thing for the third coin. Come on. Computer's acting goofy because I'm too close to the edge of the screen. Why are you doing this? Just right. Third coin. Thank you. For the third coin, we got to branch out again from each of the previous branches. We branch off twice, once for heads or once for tails for the third coin. So heads, tails, heads, tails, heads, tails, heads, and tails. But we have a fourth coin. And I don't know if I have room to write it over here. But for the fourth coin, we do it again. From each of the third coin's concluding branches, we branch out twice, because on the fourth coin can come out one of 2 ways, heads or tails. So you can see this tree diagram is getting pretty congested, but it shouldn't surprise you that there are 16 branches, because the first coin can come out one of 2 ways, and then the second one 2 ways, and the third one and the fourth one. Fundamental counting principle says that there are 2 times 2 times 2 times 2, which is 16 ways we can flip these 4 coins. I'm going to pause this and label all the H's and T's on the bottom. Drawing a tree diagram for flipping coins over and over and over again can be a little time consuming. So here's some advice from me to you for my students. I would have a tree diagram in your notes for flipping 2 coins, which means that it would just be this part. Give me 1 second to highlight it. That's a 2-coin tree diagram. For flipping 3 coins, which would be this part. And it wouldn't be a bad idea. Let's move that up just a little bit. Part in the green square. And it wouldn't be a bad idea to have in your notes a tree diagram for flipping 4 coins. The 2-coin and the 3-coin tree diagrams are embedded in the 4-coin tree diagram, because think about it, it makes sense. You have to flip 2 coins in order to flip 3. You have to flip 3 in order to flip 4. So it totally makes sense that it's in there. Let's get rid of that square. But I would have that in your notes. I hope you can read between the lines. All right, so now that we have the tree diagram, we can use it to answer the question. It is worth noting that there are 16 branches across the bottom, which means all of these probabilities that we're about to calculate are going to be out of 16. All we have to do now for each one is count how many of the branches at the end satisfy the event in question. For example, the first one is we get all heads or all tails. So we just have to find the branches that represent all heads or all tails. That's not that hard. If we're going to do all heads, then it must be heads, 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 heads. So there's one branch. And where's the all tails branch? Tails, 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 tails. Only two of the branches are all heads and all tails. So let's write that on the previous screen, 2 out of 16. Let's see, we'll put that in red. Of course, that reduces to 1/8. If you wanted to make a decimal out of it or a percent, it would be 12.5%. Always read the instructions in the work so that you know how they want you to write your answer. Okay, part B, you get the same number of heads as tails. Well, we flip 4 coins, so if we got the same number of heads, that means 2 heads and 2 tails. All right, this one's going to take a little bit more work. But instead of starting at the top and going down, let's just go to the end of each branch and see what they represent. So starting with this branch here. Well, we know this one is all heads, so it's not 2 of each, so we can skip that. What's this branch represent from top to bottom? H, 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 T. That is not 2 of each. What is this branch? H, H, T, H. That is not 2 of each. Just keep going. What is this branch? H, H, T, T. That is 2 of each. We're going to keep that branch. What about this branch? H, T, H, H. That is not 2 of each. We don't want that branch. This branch. Remember, just start at the top, work your way down. H, T, H, T. That is 2 of each. Same number of heads as tails. We want that branch. We'll leave its node at the bottom highlighted. It's actually what you call the dot at the bottom. Is this one 2 heads and 2 tails? H, T, T, H. It is. We keep that one. Is this one 2 heads and 2 tails? H, T, T, T. It is not. We don't want that one. Next, T, H, H, H. That is not 2 of each. Next, T, H, H, T. That is 2 of each. We keep that branch. This one. T, H, T, H. That is 2 of each. We keep that. This one. T, H, T, T. That is not 2 of each. We don't keep that one. This one. T, T, H, H. That is 2 of each. We keep that one. This one. T, T, H, T. That's 3 tails and 1 heads. We don't keep that. This one is 3 tails and 1 heads also. And the last one, of course, is all tails. So it looks like there's a total of 1, 2, 3, 4, 5, 6 branches that have 2 heads and 2 tails each, which means there are 6 out of 16 ways to flip 4 coins and get the same number of heads and same number of tails. Let's write that on the previous page. 6 out of 16 reduces to 3 out of 8, which is 37.5%. Now, just as a side note, some of you might be thinking, isn't there a way to get that 6 without the tree diagram? Yes, and it actually involves a technique we've already talked about, because if you think about it, what we're really asking is how many permutations do we have of 2 heads and 2 tails? Well, this is like the Mississippi problem. When you have permutations with repetitions, it's the total number of objects divided by factorial, divided by the factorial for the count of one of them, 2 heads, and the count of the other. But if you did that math, you would end up getting 6. So yes, it is possible to do some of these without the tree diagram, but it's nice to have multiple ways to approach a problem. All right, C, you get at least 2 heads. All right, so at least 2 heads. That means I can get 2 heads, 3 heads, or 4 heads. So I can get 2, 3, or 4 heads. Okay, let's go to the tree diagram and find all the ones that have 2, 3, or 4 heads. All right, here we go again. Does this branch have at least 2 heads? Yeah, it's got 4. Keep it. In fact, every one of these has at least 2 heads. How do you know? Because every one of these starts H. Oh, I take that back. I take that back. Every one of those 4 has at least 2 heads because they all start out HH. So moving to the next one, does this one have at least 2 heads? Yes. Does this one have at least 2 heads? HT, it has 2, it's okay. Does this one have at least 2 heads? HTTH, yes, it has at least 2. Does this one? No, it only has 1 head, the rest are tails. So almost all of the first half has at least 2 heads. That makes sense because the first flip was a head. So it only needed to pick up 1 more. But the next ones, let's see. Does this have at least 2 heads? THHH, yes, it's got 3. This one, THHT, yes, it's got 2. Remember, we're looking for at least 2. This one, THTH, yes, it has 2. Does this one, THTT? No, it only has 1. Does this one, TTHH? Yes, it's got 2 heads. Does this one, TTHT? No, it only has 1 head. And the last 2 won't either because they start out with 3 T's. So the most it could have is the 1 head, which this one has, but it's not enough, and this one has no heads. So it looks like there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 branches that have at least 2 heads. Let's put that in our answer. At least, 12 of the 16 outcomes have at least 2 heads. That reduces to 3/4, which is 75%. A quick comment about this one. We could have also done it with complements, because what's the opposite of getting at least 2 heads? What's the opposite of getting 2, 3, or 4 heads? Well, 0 or 1 head. So we could have said, well, let me find the number of ways that we can't get at least 2 heads, that we get 1 or 0 heads. Well, none of these because they already have 2. And if we do that one, then it's got to be that, so this branch. And then to have 1 or 0 heads, here's one of the branches that does that. Here's another. Here's another. And then there's another. It shouldn't have been that many, which makes me think I miscounted on the previous one. All of these have 0 or 1 head, correct? Yes, that's 5 of them. There were 12 in the other. That means I miscounted in the other. You know, I'm kind of glad I, on the fly, said, let's try the complement because I should have only gotten 11. All right, give me 1 second here. I'll have to go back and rewatch the video because I don't want to re-record it at this point. But I'll put a note in the description in the video on YouTube that there was a mistake at this point and it's rectified at whatever time point this is. But it looks like there's really only 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 branches that have at least 2 heads. I'm going to double check by tracing the ones I don't have to see if they don't have at least 2 heads. This one only has 1. This one only has 1. That only has 1. That only has 1. And of course, this one has none. So looks like I made a mistake. But I'm human. Stuff happens. I could totally erase the video and start over. But as I've said before, it's okay to make mistakes. What's not okay is to not learn from them. And it wouldn't surprise me if there were mistakes that I made that I didn't catch. And if you ever watch one of my videos and spot a mistake, put a comment in the comment section, or if you have my contact information, send me a message. I will go do something about it. But, you know, it happens and you learn from it. Life's full of mistakes. What are you going to do about them? 11 out of 16. I should know what that is as a percent. 68.75. At least we caught that. All right, let's see if we get this last one. You get at most 1 tail. You get at most 1 tail. Well, let's think about what that means. At most means no more than that number. So at most one tail means 0 tails or 1 tail. You can't have 2, 3, or 4 because it can be at most 1. So in the tree diagram, we are looking for the branches that have 0 or 1 tail. Oops, all that's still there. Give me 1 second to get rid of it. All right, let's find the branches that have at most 1 tail. In other words, have 0 or 1 tail. We'll use blue this time. This first branch, because it has no tails at all, so it's good. The second branch only has 1 tail, so it's a keeper. This third branch has at most 1 tail. It's got exactly 1. But not this one because it's got 2 tails and we're looking for the ones that have at most 1. So we don't want that branch. Maybe I just forgot to delete a bad branch earlier and that's why I made a mistake. This branch, does that have at most 1 tail? Yes, it's got exactly 1. We keep that branch. Does this branch have at most 1 tail? No, it's got 2, 1 here and 1 here. We want at most 1. It's got more than 1. So we don't want that branch. This branch, no, it has 2 tails. We want at most 1. This branch, no, it's got 3 tails. We want at most 1. Does this branch have at most 1 tail? Yes, just the one at the top. I believe the rest of them will fail. This one has 2. This one has 2. This one has 3. All these on the right will have 2 because they start out tail. So we don't want any of those. So it looks like 5 have at most 1 tail. Come on, let's cooperate. 5 have at most 1 tail, which is going to be 31.25%. How did I know that one? Well, I knew that those added up to 1, so I knew those added to 100%, and I just did a subtraction problem real quickly. All right, so despite the mistake that I make, I hope that you can kind of follow how a tree diagram works for flipping coins. You simply have to have 1 layer of branches for each coin that you flip, and when you're flipping coins, each time you have a new branch, you take the previous branch and you spread out 2 branches, 1 for heads, 1 for tails, and then you just do that all the way down.